Chapter 6 of our ECE 301 workbook is solely devoted to the concept of superposition, or more notable, the superposition principle. So the idea here is that suppose you have a circuit of resistances with linear dependent sources. That would mean, for example, a current controlled voltage source with just a single constant gain parameter, for example, and n independent sources, voltage or circuit or current. We call a current flowing through a circuit element, and we're voltage calls it a response. Okay, so response refers to the current. Okay, recall that we zeroed independent sources to determine Thevenin resistance of a two-terminal circuit. And suppose we zeroed all the independent sources of a circuit except one and observe a particular response, current or voltage, and denote the value of that response, R1. And then proceed in like manner where we just take in turn zeroing all the others, okay, including the first one out, and then call that response R2. And then summing all the responses in this way, we could generate the total response, say R sub T, for a circuit element. So the idea here is trying to find the voltage or the current associated with one independent source at a time, right? So superposition principle simply stated as this, that the total response and the sum is the sum of responses to each of the independent sources acting individually. So for example, you would get the response from zeroing out source one, and then have that, and then the zeroing out source two, and so forth. Excuse me, let me say it again. You would zero everything out but the first source and get that response. Zero everything but the second source and get that response. So you're zeroing everything except one. So it's just one that's remaining. So we're going to illustrate sort of and build a methodology for this approach and then apply it with a couple examples by starting with this example here. So what we have here is exactly the situation we wanted. We have an independent voltage source here. This is a dependent current source depending upon the current flowing through the R2 resistance, and you have another independent current source over here. So you have two independent sources and you have one dependent source there, and of course two resistances. So suppose our goal is to find the voltage across R2 here, which we're denoting as VT, okay? And what we'll start off with is just what would the Kcl equation, again, applying node voltage analysis, if we're applying NVA and generating a Kcl equation for the top node, what would it look like? So in other words, we are writing currents, okay? And we're summing, let's sum the currents to zeros. So again, we'll do sum of outgoing currents and set that equal to 0. So starting here on the far left over here, we would have minus IS2, okay? And then of course you'd have the dependent one coming down plus KIX. Then we're assuming the voltage here, the nodal voltage there is the same as VT, all right? And then we're going through that resistance R2 there, or just Ohm's law there, which is say if this is just representing the current through there, and we know this voltage and we know that resistance, we can just use Ohm's law and say, well, we know that that has to be VT divided by R2. So we don't need to write a ground or anything in that case. We just use Ohm's law. And this one, if assuming that is the same, again, the voltage here and this node is the same here as VT, then it goes from VT to VS1 through that resistance. And so there we would have VT minus VS1 divided by R1, and we would set it equal to 0, okay? So again, we're assuming the voltage through at this node up here, at this top node we're going to assume it's VT, okay? All right. And if we rewrite this and solve for VT, okay, what we would get is the following. I've already done this algebraically just to save some time. You're going to get two fractions times both of those sources. One of them will be the second resistance over the sum R1 plus R2 plus K times R1, and that will be multiplied by the voltage source 1. And then you will have another fraction, R1, R2 in the numerator, with exactly the same denominator, R2 plus K times R1. And that would be multiplied times the currents, independent current source, IS2, okay? So what this is saying is that just by solving for the goal of finding that voltage through that resistance, all right, then we could get it in two components, or at least there's two terms that we could find it from. So we either get a fraction of the voltage here, or we're getting a fraction of the current there to determine what the voltage is. So the idea with superposition is to nullify one of these sources. In other words, if we zeroed out the current source, then this would be the response that we would get. If we zeroed out the voltage source, this is the response we get. And then we simply would add those two responses and obtain the voltage that's desired, okay? That's exactly what superposition is, right? So, but just from a formalistic standpoint, this is the bottom of page 76. If we go on to page 77 and were to write each of these terms out, what we're saying is that the first response, V1, would be obtained by setting, we'll put it over here, if we're setting the current source equal to 0, then that response is that first fraction, R2 over R1 plus R2 plus K times R1 multiplied by VS1. So I'll put multiply VS1. And the second response was the other fraction, R1, R2 over that same denominator, but that would be multiplied by IS2 because this would correspond to setting the voltage source equal to 0, okay? So this is the idea. And then so therefore, clearly, if you were to determine these independently and add them together, you would get what we just had on the bottom of page 76, okay? So that's what superposition is all about. Zero everything out except 1 and get that response for the parameter that you're looking for, okay? And then keep doing that across all the independent sources. It's very important to notice that you don't get any terms involving dependent sources. That KIX term never occurs in this, notice that. So the goal here is don't zero out dependent sources. Never zero those out, leave them in there, okay? They're not going to contribute any problem to the individual responses we're looking for. Just for definition purposes, a linear controlled source is one in which the control is defined by a constant times a certain current or voltage elsewhere, just like the K times IX. That's a linear controlled for the current source, right? And certainly if you look at Ohm's law, that is a linear equation because it shows a linear relationship between the voltage and the current. But nonlinear equations have forms like this, where the variables involved are not just simple scalars times their first power. So you've got squared powers here or quadratics. Here you have trig functions, or you may have exponentials. Those are not linear controlled sources, all right? So one thing to realize is that the superposition principle does not apply to any circuit that has elements defined or controlled by nonlinear equations, okay? So the assumption with superposition, this adding responses of, is assuming that all the controls associated with dependent sources are linear, okay? Nothing with squares or sines and cosines, things like that, okay? So that's important. Those are the conditions we need to have before we apply it. So let's look at example 8a, the bottom of page 77, and apply this principle. And I think you'll like this. It's very, very straightforward. It's easy to implement because we know exactly the strategy is to zero one source out of it, to leave one source left at a time. So here we're assuming that we have 2 amps on this current source. And so the first thing we're going to do is, our goal is to find this voltage here, right? That the voltage through the 5 ohm resistance, right? So we will start off by zeroing the 2 amp source. And then again, you have to remember, what does it mean to zero out a current source? So remember what that means is we replace it with an open circuit, okay? So then we'll redraw this. So the first response will be obtained from this circuit with the current source removed. So we'll put our resistances back in as they originally were. And again, this is, now we're going to call this V1. Keep the polarities the same, but we have zeroed out that current source, okay? So notice I didn't put VT here, right? So this is saying this is the first response for VT. So again, our goal is maybe down here at the bottom, we'll just make a mention. We're going to obtain it as a sum of 2 responses. Why 2 responses? Because you have 2 independent sources, okay? So the number of terms in this sum will be how many independent sources do you have, okay? Because you want the response associated with each of them separately. So right now we're just trying to get the response associated with the voltage source, and we're calling that V1, right? So, but now we're only going to pay attention to this loop right here, and we have a voltage source, and again, there's no current flowing here. So just paying attention to this very closed path here, you've got 2 resistances, yes, that are in series with each other, and this voltage source. So you could apply VDP, voltage distribution principle here, and know immediately that V1 must be that 5 ohm resistance over the sum, 5 plus 10, times the voltage source, which is 15 volts, and that would give you 1/3 times the 15 volts, so that's 5 volts. So therefore, we know the first response down here is 5 volts, okay? So that's what we know thus far, right? Then what you do is then zero, so we'll be zeroing the 15 volt source, okay? Now these are done independently, so we're going to zero this one out. So this was the response due to this source. Now we're zeroing this one out to get the response due to the current source, okay? So what we'll do here is, remember, we need a short circuit. Just to remind ourselves, how do we zero out a voltage source? Short circuit it, okay? So there's our short circuit. Here's the 10 ohm resistance. Here's the 5 ohm resistance. And here is the original current source. Okay, just 2 amps, okay? Like that, right? Okay. And again, our goal is to determine V2, and we'll leave it in this direction, plus minus that way, okay? So that's our goal, right? So what can we do here? Well, this could be reduced by an equivalent. Clearly, we could get this down to 1 resistance with that current source to help resolve what V2 is. So let's do that. What's the relationship between these two? They're in parallel, right? The 10 ohm resistance and the 5 ohm resistance are in parallel. Okay. Again, we were doing this for closed networks all the time earlier. So the equivalent, which we'll call REQ, is 5 times 10 over 5 plus 10. And that should give us 50 over 15. That's going to be 3 1/3. So we'll just represent it like that. Ohms, okay? So the equivalent here is just 1 resistance in parallel to the current source of 2 amps. And that is REQ equal to 3.33 ohms, okay? All right. So we have a current coming in, and we have a resistance here. So therefore, Ohm's law. Again, for a resistance, we could get the voltage. So V2 must be the 2 amps. Again, assuming this is plus minus, where the voltage is there. So that would be PRC. We get 2 amps. So there's no need to insert a negative there. It's the straightforward Ohm's law. It's PRC. So it's 2 amps times the 3.33 ohms, and that's going to be 6.66 repeating there volts. Okay, so you've got that response due to the 2 amp source. So we add these two down here, and so the total response that we were seeking for the original circuit is just 11.66 repeating volts. Okay, simple as that. So review. You must zero everything out except one of them. Okay, if there's only two, then there's two terms here. If you have three independent sources, then you have three terms. So the complexity is clearly determined by how many independent sources. Don't zero out dependent sources. We don't have any dependent sources in this one, but just remember, leave them alone. Okay, all right. So let's move on to page 78 and get some more practice. So we're just going to get some more practice now doing superposition. Okay. In this case, we're going to use it this time to get a current. Okay, so let's just be fair. We did it for voltage before, so this time we're going to do current. So we have two independent sources. All right, we're going to assume that this current source again is 2 amps, so we'll just mark that there. And our goal is to get IT. Sometimes it's very helpful to just do this. Say, well, this is what we're going to get. We're going to get it as the sum of two responses, and then maybe just indicate which source you're zeroing out. So we're going to say I1 is the response we get when we zero the 2 amp source. And we'll say I2 is the response we get when we zero the 15 volt source. So it's just maybe a handy way of noting which is going to be, which response are we getting first, and then which one are we getting second, so that we don't get confused and keep things in order, right? So now one thing to realize is if you look very carefully at this problem versus the other one, it's the same problem, okay? So what we've done, just so I don't trick you anything, on page 77, this is the same problem, but this was the voltage source we want. But this was the voltage to this resistance. This is the same problem, but now we want the current through the 10 ohm resistance, okay? So it's exactly the same problem. So let's just use information that we had from the previous page. So we'll say from the previous example, that's why it's called 8B as opposed to 8A. We know that the response V1 was 5 volts. Again, that was the response that we got when we zeroed out the 2 amp source, okay? So it's matching with our indexing here. Subscript 1 means, did you zero the 2 amp? Absolutely, okay? That this response, this voltage response, came from zeroing the 2 amp out, okay? And the voltage response when you zeroed out the voltage source, which was V2, remember, was 6.66 repeating volts, okay? So again, very important that these subscripts are matching these subscripts so that the responses that you get are with respect to the same sources that you're zeroing out, okay? All right, so, and this again was V1 and V2, we'll say for the voltage, just repeating what we knew from last time, for the voltage response through the 5 ohm resistance, okay? I'm just repeating what we just did on page 77, okay? All right, so now let's look at the situation we're at here with getting current responses. So if we zero the 2 amp source over here, okay, then the voltage across, again, zeroing it out means, it definitely means an open circuit, right? Then the voltage across the 10 ohm resistance is we already know this, 5 plus 10 times 15 volts equals 10 volts via VDP, okay? All right, we already know that, okay? Again, we've, we looked at that earlier, but we were getting the contribution. With the previous problem, we were using VDP to get the voltage across this resistance. Now I only care about the 10 ohm resistance. So if we zero this out, I'm just saving us a drawing here. If we zero this out, now we'll use VDP and get the voltage across the 10 ohm resistance, you see. So that's why this is a different fraction. Before it was 5 over 5 plus 10. Now it's 10 over it because I'm only interested in the voltage across that one this time, right? So therefore, I know that I1 must be what? Well, in that case, there's only 10 volts going through it, right? So we'll have 10 volts over the 10 ohm resistance. So that's 1 amp, okay? Because this is zeroed out and this is the smaller circuit we're working with and the current flowing through, Ohm's law, is 1 amp, okay? Again, this is Ohm's law, right? So we already know that this part of the contribution is just 1 amp up there, right? So now let's zero the 15 volt source. Again, we can kind of logically do this, but we'll go ahead and draw this one maybe to help out. We'll zero the 15 source and consider KCl at the top. At the top node, okay? Very traditional approach. So if it's zeroed out, we've drawn this before, it's a short circuit, 10 ohm resistance, 5 ohm resistance, 5 ohms, 10 ohms, and the current source out here. Okay, all right. And we indicated before, we're going to apply KCl because all I want to know is I2. I need the contribution. I need to know in this circumstance, what is the current going through the 10 ohm resistance, you see. So it's just a matter of taking turns, zeroing a source out, and then finding the component of that current or voltage you're looking for that resulting subcircuit. So you get different circuits out when you zero these things out, and then you're just solving like multiple problems and getting their answers and adding the results together. That's all you're doing, okay? So we're simply trying to write it this way, following the same direction of the original total IT there. So that's what I want in this case, IT, okay? All right, so KCl top node, let's do sum of outgoing. You'd have -2 because that's an incoming. You would have, well, if I represent I2 coming into the node this direction, then outgoing, again, I'm doing KCl here at the top node, then I have the -I2, and then what else would I have? Well, I already know how to describe the voltage up here in this case, right? Because I did that in the previous problem. If we go back to the case of zeroing out, I just want to illustrate, we already know what this voltage is. We've already determined, there it is. So we're back to this situation again, and I know what the voltage is here. The voltage associated with this node up here is going to be V2, okay? All right, so I will have V2 plus V2 divided by 5, okay? Because that must be the current coming out. Again, that's just Ohm's law, right? We already know that the voltage response in this situation is V2, and if I know the resistance, then I got a current representation. It's just the difference. It's just it's the ratio of those two, okay? All right. Again, just so it's clear, we already solved to figure out what this V2 was. So I automatically know what the current must be coming through that resistance, okay? So set that equal to 0. What does that say? Well, that says that I2 would then have to be 1/5 of your voltage response in this situation, -2, okay? Plug in the values that we have here. we could use, rather than 6.66, maybe we'll use the fraction. So that would be 20 divided by 3 times 1/5. And that would be minus 2. So that's 20 over 15. So again, that's 20 over 15 minus 2. That's same as 4/3 minus 2. So we would get negative 2/3 amps. Okay. All right. So this term right here is negative 2/3 amps. That's the response of zeroing out the voltage source. Therefore, the total result here by superposition, I'll just write it over here on the side over here, by superposition, the original current we're looking for is 1 minus 2/3 amps, which is simply 1/3 amp. And that's the answer. It's a 1/3 amp that flows through the 10 ohm resistance, okay? Right. So again, it's important that the reason we're able to do this is this problem 8b is because we already did the work in 8a to get the voltage responses. So it's very possible when you're doing superposition, you're going to have to go through an assessment of what kinds of responses you're getting. What are the voltage responses of zeroing everything out except 1? What are all the current responses you're getting when you zero everything out but 1? And then collect those as you need them, all right? It just depends on what you're solving for, right? So let's do it again, all right? Add a few more resistances here. In this case, we have 3. And this time, we will do the whole thing. We're going to look for a current and a voltage, but they're not associated with the same resistance, okay? So again, we're going to go through the process of zeroing things out as we need to. So our goal is to find the current through the 10 ohm and the voltage through the 5 ohm, okay? Right, using superposition. Let's start by making the 20 volt source active and zero the 10 volts. So these are both voltage sources, notice that, okay? So, but we're gonna call the first response obtained when you zero this guy out, okay? So that's gonna be our first goal, is to zero out the 10 volt source with a short circuit. So let's do that, okay? Again, we're getting our first response, I1 and V1, from zeroing this one out, okay? Zero out for V1 and I1. So this is why it's important to keep your indexing straight. Which ones do you get according to which source you're contributing? In this case, another way to say it is that we're really looking for the responses, the voltage response and the current response for this source. There's only 2 here, right? So if there were 3 or 4, you'd zero everything out except for this one, okay? But just to keep it straightforward here, we're only doing 2 sources, but the idea here is that these are, I should say, these are the responses for the 20 volt source, okay? That's a better way to think about it. The 1, 1 index means this is the first source we were associated the response with, okay? So you got to zero everything else out. Okay, let's go back. Just want to make that clear. So we're going to zero it out. We're going to put our 10 ohm resistance in. This will be our first current, I1, we're looking for. And through the 5 ohm resistance, I'm looking for a V1 response. So notice how we did that. So we're now indexing according to which source contributes the response, in this case, the 20 volts. Still have to put in the 15 ohm resistance here, but you've short circuited out the other source, okay? So this is the important part right here. Now, those are the appropriate labels that we need to use to get those responses associated only with this one independent source. So let's try to do some equivalents here and get this thing a little bit simplified here. What relationship do we have between resistances? Looks like clearly the 5 and the 15 are in parallel. Let's make a note, 5 ohm, oops, 5 ohm and 15 ohm are in parallel. So let's go ahead and get our equivalent. Our EQ then is 5 times 15 over 5 plus 15 ohms, right? That's going to give us 75 over 20, which is 15 over 4, which is 3 3/4 or 3.75 ohms. Awesome, okay? So then we have reduced, with the one equivalent, we have this reduced to a 20 volt equivalent source, and we have the 10 ohm resistance, and now we have an equivalent, okay? Which is 3.75 ohms. But the voltage through that is still, whoops, that's negative, is still V1, right? Because these two are in parallel, the voltages across them are the same, right? So that's why even though I've written this as 3.75 ohms, I'm still finding that voltage response that matches what I originally wanted because they were in parallel, right? So let's just use VDP then, because now we're in series with the voltage source. So VDP applies, voltage division, and we're wanting that response. So it'll just be that numerator 3.75 over 10 plus 3.75 times the 20 volts. And with a little algebra there and a calculator, it's 5.45 volts, right? So there we have our first response for the voltage, okay? So V1 is the first response to that needs to be added to a second voltage response to get the total for V sub t. Let's go ahead, though, we're not done. While we're here, let's go ahead and get the I1, all right? So similarly, the voltage through the 10 ohm resistance would have to be what? So also, we'll say by VDP, right? The voltage, now we didn't write it, we didn't index it, but we'll say the voltage through the 10 ohm resistance, right, must be what? Okay, well, same thing, but use 10 in the numerator. Same denominator, right? So we're just using VDP again. That's the proportion of the 20 volts from the source. And if we simplify that one out, clearly that's going to give us 200 over 13.75. And what we'll have here is this in volts, right? And I'm just going to leave it like that for now. I mean, there's no need to simplify it because I'm going to multiply I'm going to divide it with Ohm's law. So that gives us the voltage across it, and I have the 10 ohm resistance. So via Ohm's law, what I1 has to be is 200 over 13.75 divided by 10, voltage divided by the resistance, and that will simplify as 14.54 over 10, or 1.54 amps, okay? Again, VDP got me the voltage across it. I already know the resistance, so therefore I know what the current must be through it, okay? So this is the I1 response associated with the 20 volt source, okay? So we're halfway done for both of them in terms of superposition. So let's move on, okay, finally to page 79. And now we will make the 10 volt source, okay, active and zero the other one out, okay? So if we're zeroing the other one out, let's just draw it where it's been zeroed out. And we have our 10 ohm resistance. We have our 5 ohm resistance. And we have our 15 ohm resistance up here. And we have the other voltage source this time, plus minus. So we're looking at the response due to that source. The other one's been zeroed out, okay? And yes, that's exactly right, what you were thinking. Now we'll call that V2, right? and we'll call this current through that resistance I2. So we just changed the subscripts, right? So we just created a simpler problem, just like we did before, and we just now solved this for those two components, right? Again, what can we do to resolve make this a little bit easier to get that voltage? Notice the relationship. We still have some parallelism here. This time the 10 ohm and the 5 ohm resistance are in parallel. It was the other way around for the 15 and the 5 before. So this time the equivalent is going to be what? 10 times 5 over the sum, 10 plus 5, and that will be 10. I'm going to leave it as 10 third ohms because we'll have to do some multiplying later, right? So 3 1/3, okay? All right. So let's just clean this up a little bit. Leave the 10. This then has an equivalent now. We have 10 volts on this source. Still have the 15. Let's write it this way, 15 ohm resistance there at the top. And now we've combined these into one here. So here we go. There's the equivalent. And this equivalent REQ was equal to 10 third ohms. And then the question is this the same voltage, V2? Yes, because this equivalent came from two parallel resistances, which means the voltage across them is shared. Current is shared for series, voltage is shared for parallel, okay? So now we can do VDP again, because I now only want to know the voltage across this guy, all right? So V2 in this case is 10 thirds divided by 15 plus 10 thirds. So you might need a little calculator here. And that's the proportion of the 10 volt source, right? We will have through that resistance there, which would correspond to the voltage through the 5 ohm resistance. And if we do a little calculation here, you should get 100 over 55, a little less than 2, so it's about 1.82 volts. There we go. We are, okay, almost done. That now we already have the answer for the first part. So we can go ahead and write this down here at the bottom. We know that the sum of the responses for that voltage through the 5 ohm resistance is 5.45 plus 1.82 volts. And that's about 7.27 volts. So halfway done. Over here, we have I1, we just need to get I2, right? So maybe just to set it up, we know it's equal to 1.45 amps plus something, okay? And that's what we're trying to determine right now, right? So we now know from VDP what the voltage is there, all right? So therefore, we could do VP again, all right? And say we also know the voltage across the 15 ohm resistance would be what? Well, this is VDP again, because these two resistances are in series, correct, with that voltage source. That's VDP. We're just getting the other term. Don't have a label for it right now, but we'll just get the calculation for it. So that would be 15 over that sum again, 15 plus 10 thirds times 10 volts. And that proportion turns out to be something like this, 8.18 volts, okay? Now, somebody might have said, well, wait a second. If these two things are in series and you just told me that the 1.82 goes through V2, then 10 minus whatever that is must be what's left here. Absolutely right. So this is just a check on our answer that if you sum these two, you better get 10 back, right? But if someone just said, I don't need to do VDP, if I only have 2 and I've got this voltage, then I know what the other resulting voltage is, okay? Law of conservation of energy, absolutely, okay? So we're gonna know what that is, all right? So we now know what the voltage is now at that 15 ohm resistance, okay? All right, and let's go back and do KCL to see if we can get that I2 now. So we're gonna come back and do KCL here, okay? Okay, all right. So just to make a note here, we're gonna apply KCL. Again, we're looking at the case with zeroed out the 20 volt source, looking at only responses due to the 10 volt source. So we're applying KCL to the top node, right? And let's do that. So now I just want to represent currents, all right? So one of them, if we're representing, again, if we do sum of outgoing, just so we can make sure we're consistent, sum of outgoing currents equals 0 is our approach. If I2 is coming in to that node, then we obviously have to have a minus I2 as an outgoing one, right? Okay. And thinking about, well, do I know the voltage? I need to represent this voltage at V2 and take it over to 10 through the 15 ohm resistance, right? So, and then I need to take it through the V2. Or I can use Ohm's law here because I already know what the V2 value is. I've already calculated it. It's 1.82 volts. And if that's 5 ohms, then I know exactly what that current is, right? And it's PRC, so it's coming outward. So it is coming outward. The current is going from the top to the bottom, and I know where the voltage is. So I'll just go ahead and write that value. So that's going to be plus 1.82 volts divided by the 5 ohms. Okay. So is that clear? This is not MVA in this case. This is just flat out Ohm's law because I know what the voltage is. If I know what the voltage is and I know what the current is, I always know and I know what the resistance is. Ohm's law, I know what the current is. And we're assuming it's PRC because that's a resistance. So it's outgoing. Perfect, right? And then now I need a representation of the current going this direction, but now it's going from a voltage through a resistance to another voltage there, right? So in this case, it's the 1.82 minus the 10 volts, okay, through the 15 ohm resistance, okay? So again, we know what the 1.82 value is, right? And in fact, we kind of figured this out a minute ago. So what we really have across the 15 ohm resistance is 8.18. So we could have gotten it that way too. Either way is fine, right? And this is equal to 0, okay? So this value here, again, is negative 8.18, okay? We already know, again, this is the same thing. I could look at it either in terms of MVA, voltage to voltage through resistance, or the fact that I already know what this is, but it has to be outgoing, okay? And if it's outgoing, in this case, the representation of this voltage is going to have to be negative, okay? All right? Because for this to discharge the 10 volts, the current has to come in, see? If it's coming in, that's an incoming, so that's why this has to be negative, right? Okay, because this energy has to be distributed, supplied. So that means we know the current has to be entering the negative polarity here, so it's coming inside there, not out, all right? Okay, so if you do the algebra here and collect all the values here, what you will show is that I2 with some algebra there is going to be negative 0.181 amps, okay? So in fact, the reference direction chosen here is wrong in the sense that the current is really flowing out. But if you think about it, that kind of makes sense because the current flow should be coming into the negative pole here, right to left, distributes down to make this PRC. This was PRC, this needs to be PRC, okay? So it actually makes sense. And usually that's what happens. Nothing wrong with taking the current reference direction that direction. But in this case, for that source is actually reversed, all right? So the final representation of current has to be the 1.45 amps going left to right, mitigated by -1 or 0.11 amps going the other direction. And so we would subtract here 0.181 amps, and you'll get 1.269 amps. That is your total response. And it's positive, so the net, if you want to go back to the original problem, right, which we had back on page 78, it's just saying that for the total response is in fact going the correct direction there. But when you're only applying finding the response from this source, it's really the other way. That response is opposing it, okay, right? So again, superposition, just be careful. It's like having subproblems that you have to resolve. Just keep your indexing consistent so that you know which term is being added to which term. The V1 and the I1 came as a pair when we zeroed out the 10-volt source, and the I2 and the V2 came about when we zeroed out the 20-volt source.